We're going to do one of the classic material science experiments of physics. We're going to find the Young's modulus of a material, and what that is to find the physical properties of the material. We're going to take copper, so I've got a thin copper wire here, and the reason we're going to be able to do that is because it's ductile, it's quite stretchy. It will have a measurable stretch when we do it. So Young's modulus is basically how easy it is to stretch the material or compress the material. We're going to stretch it this time. So the basic definition is stress over strain, and stress is what we do to the material. So it's how much force we put on it, but it's how much force we put on per square meter. So a thin wire like this won't have much area, so it won't need much force to make it stretch, which is good for safety, but also makes it easier for readings. The strain is how much it stretches. So it's basically its extension to original length ratio. So if it stretches by, let's say, 5%, then along the length would obviously give us more stretch. So it's this idea of ratio to find out how much it stretches compared to its original length. Now we've put them into the equations using symbols. Then it's force over area, cross-sectional area across the wire, and its extension over the original length. And if we do that and rearrange it more cleanly, then we end up with flax, where force and length, area and extension go into it. And that will give us this value for Young's modulus, which will be huge. It will be gigapascals, okay, or giganewtons per meter squared. I point that out quickly because the extension and length are both meters, so meters divided by meters down here, nothing happens. Force, newtons divided by area, force per meter squared, newtons per meter squared. That's also in pascals, so quite commonly done in that. So the basic setup is that we're going to need to put tension in our wire, so I'm going to hang weights onto this part down here, and I'm going to increase those, and this wire will stretch. And the wire is very long, so I'm going to get a big extension. It's also very thin, so it doesn't need much force to make it happen. Okay, and because the measurements are going to be small, then we're going to need some delicate instruments. So we're going to be using two things. One, the micrometer, which is to measure the diameter of the wire. If we measure the diameter, we can work out cross-sectional area because it's going to be spherical, or circular cross-section rather. And then here, what we normally use is a travelling microscope. That's quite hard to video. So what we're going to use is vernier calipers, and it will give you a chance to work out this scale again. Okay, so millimeter scale, we're going to look down here and then use this vernier scale at the bottom to actually work out how much it's stretching. And what I'm going to do is I'm going to take a little marker, which I've put on there, a little blue marker, and I'm going to see how far that stretches, how far that moves along as we add force. So we're going to get a range of results, and from that we can end up with a lovely graph which will give us an average value, a much better value for Young's modulus. So I need several readings first, one of which is the length. Okay, so we're going to look at that, and some people get confused about this. We want to know how much it's stretching, so if I put my marker at this end, far away from the clamp, then that end's not going to move. It's this end that's going to move as I put more weight on, so I'm going to put my marker quite near to the end. So I want the original length from that point up to this end here. So it's lying on top of the block, so what I'm actually going to do is measure the distance from there, and let's see if we can get it to stay. Oh no, it's not going to, so I will take the measurement in a second. Okay, the length that we've got there, the original length, is going to be 2 meters 76.8. Okay, so 2768. And what we'll do is we need that in meters. All of our units need to be in meters. Okay, so 2.768. I'll add it onto here. 2.768, and the other thing that's fixed is going to be our cross-sectional area, so we need the diameter, okay, and from that we can get that into meters squared. So again, we're going to need to take our micrometer and we'll do it up with the ratchet, this thing right at the end here, so that it doesn't go too tight, doesn't crush our wire. And the dimension for that is right there. Let me just try and get it into focus. So it's a bit more than, it's pretty much just about 0.5 millimeter diameter. You can see that because you can just about see the half there. But notice the reading is a bit less than 0. Those are hundredths on the thimble. And also don't forget, if we take it back, it doesn't quite line up, okay, when we have nothing in the jaws. So that's actually small 0 error, and you actually have to add that on. If you want to be really precise, then that's, I would say, about 1/3 of a 100th of a millimeter extra. Now we need to do this in several places. If I measure it in a different spot, then we can average them, of course. The wire may be crushed in places. Other students have had a go at it, let's face it. So it might be a little bit there. So if I, there we go, get the light better on that one, that's a second reading. And if I just take a third one right near the end, that might give us a better shot as well. So again, if I turn that, ever so slightly different again, but yeah, there's our datum scale, so it's just below that 0, so it's a bit less than 0.5 millimeter, even with the extra bit added on. So take those 3 readings, average them, and then that's going to give you your diameter, which goes on to here. So when you have decided what your diameter is, that's going to be in millimeters. So write it as whatever your scale is times 10 to the minus 3, because then when we want the area, when we use pi r squared, you've already got the times 10 to the minus 3 in. So don't try and do it in millimeters and then try and work it out afterwards. Actually put it into meters first, and then put all of that value into that bit there to find your area in meters squared. Much easier than trying to do the hard maths and trying to guess where the decimal place should go. Okay, so put it into meters, then do the maths with it. Okay, and you should end up with something around about 10 to the minus 7, 10 to the minus 8 meters squared. Okay. Okay, so there we have our first reading. We've got it set at 0, and again, just remind you, ignore that top scale there. That's unfortunately in inches. All instruments come in them. What we've got is the main scale along there in millimeters, and then this is our 50ths of a millimeter, in other words 0.02. So each one of these 0.02. So at the moment it's 0, and so that's marking the edge of this blue marker there. If I put on my first 100 grams, I already had 100 on it just to make the wire straight, but we're going to ignore that and take this as our first reading. So what we've got there, just twist that around a little bit, is a scale where it barely seems to have moved. What I've got is a slight adjustment built in, and you can just pull it along. Potentially you've got that first reading there. It's going to be very dodgy. It'll start stretching more. So if we look at that, it's obviously between 0 and 1 millimeters. It's near enough 0. So it's down at this bottom end of the scale because it's only just moved. And what you are looking for is you're looking for any line on here, on this vernier scale, that lines up with any line on there. So for me, I would say that that looks around the line about there, or possibly there. I'll say nearer this next one. So that is 36 hundredths of a millimeter. So I would say that that reading at the moment is 0.36 millimeters, because the 36 line on this vernier scale lines up with one of the lines there. Now if I make it up to 300 grams, again you'll need that as a force, because the equation was force, so multiply that by 9.81. Near enough 3 newtons, but use the exact value, it's much better. As we add more you'll see why. And again on this one, the blue has definitely moved, so I'm going to say that looks more like it. So it's almost 1 millimeter there. Again, it's almost at the top end. So you're looking for any lines here that line up. So if you take that results, to me that looks to be around about 82, possibly 84. Okay, so that'd be 0.082 or 0.084. That's the last one I'm going to tell you, but I will do the adjustments for you. So we're now going up to 400 grams. And again, it's moved a little bit. I think that's pretty much line up. So it's a little bit over a millimeter, so it's now 1 point. And again, whichever of these line up somewhere down this bottom end. Okay, freeze the video if you need to take the readings as you're doing it. 500 grams. So again, the blue has moved a bit more to about there. And we're not quite 2 millimeters. So for all that, almost 3 meters of wire, we've only stretched it coming up to 2 millimeters. But that's not a problem. That's very good. Now, what we can do is we can take those off. And if I lift those weights up, that should relax back to its original position. It's worth checking that every now and then, because what you need to do is you need to think, has my wire been permanently stretched or not? If it goes beyond the elastic limit, then you've into territory that you shouldn't really be doing the maths on. Okay, so that is now 500 grams. 500 grams. And that's taking up to round about there. So again, not quite 2 millimeters. So somewhere at this top end, somewhere around the 9, I'd say. Now 600 grams. Now you can't race through these because it does take a little while to settle in. Metal you stretch and then it stretches the last little bit more slowly. Okay, but using that looks pretty good. So we're now over 2 millimeters, just a bit over. So again, take your readings. That is for your 600 grams. Gonna go to, if it'll go on, 700 grams. Again, that's about the reading there. So 700 grams. That one's 800 grams. A little bit too far. There we go, 800 grams. So you're getting up towards 3 millimeters of stretch now. That's 900 grams. Let's stretch the meter. A little bit too far. So I'll say that's 900 grams. Possibly a little bit more. Yeah, so 900 grams. Then up to 1,000 grams. So 1,000 grams is on now. Let's adjust. And again, we can take that result. Now what I'm going to do is I'm going to relax these, so the wire will move, but don't worry, that will be stayed in its position. And what I'm going to do is relieve it of some of its weight. Not that much weight. And again, you should see now that the blue has stretched a reasonable amount. It near enough lines up. Yeah, it lines up with the right hand jaw. So, going to go back up. Going to put on, okay, back up to 1,000 grams. We'll stick on another one. Obviously, I need to be careful that I don't end up snapping the wire. So that's 1,100 grams. Say freeze it if you need to take the reading. That's now gone up to 1,200 grams. It may look a bit off from the video, but I'm looking from the same position each time, looking down on the blue marker, so I'm getting the same. So 1,200 grams. There we go. I've just added another, so that is 1,300 grams. Take that back. 1,400 grams. That's not shifted. Now you might find it's starting to not stretch as much. 1,500 grams there. If it's not a fresh wire, it might have annealed. Stretching and compressing metals tend to actually change the bond between change the atoms, so you get slightly different results. So we're up to about 4 1/3 millimeters there for 1.5 kilograms. I almost ran out of weights then, so I'm just going to come back. I'm going to take off 1 kilogram. Okay, and so it should go back. And what I really should do is I should take these readings going backwards. So I should take 10 grams off at a time and see if that works. But I'm just going to go a little bit higher first. Okay, so that's my 1,500 still. I'm going to go to 1,600. Okay, so 1,600. Luckily I have a pad underneath, so I can't put my foot there. So I missed that. Okay, so that's a bit of a stretch. That's 1,700 grams. We're now a shade under 5 millimeters by the look of it. Very, very close, but pretty much on. You could possibly say it's exactly on, maybe. And last one, 1,800 kilograms. Let's adjust that to there. Okay, so that's 1,800 kilograms. What we're going to do, just to double check, to make sure it's all right, we'll go backwards. So 1,800 will only have one reading. But there you go, it'll work. Should still work for the others, so you can double check the readings. So that is 1,700. Oops, wrong way. 1,600. I'm trying to do it very delicately because you don't want to the wires. Any shocking will increase the forces. So that's 1,500. Let's big jump there, ignore that because I'm just swapping large masses for small ones. So that's 1,000. 1,400. 1,300. 1,200. 1,100. Didn't seem to be much of a change that. And lastly, for this section, 1,000 kilograms. So there's 900. $800. Adjust. That's 700 grams. $600 grams. That's 500 grams on that spot. $400 grams. $300 grams. Again, these are all going to be give or take 2 or 3 intervals, but well, we should get a nice pattern. That's 200 grams. Ooh, bit of a change there. That's 100 grams. And that's back to 0. So if I just ignore the fluff on there, you can see that changed quite a lot there. Now you could argue it's not quite back at 0. So we do seem to have a little bit of permanent deformation, permanently deformed, but to me that's looking to be a very small amount. Okay. Okay, so take those, plot them against the force. What you'll find then is that you'll end up with a graph. And the easiest way to do it is, and I shall zoom back out with this. Okay. Okay, so if you plot force against extension, you could argue it's the force to give you that extension, so you know it's 2 ways around looking at it. But you'll end up with, excuse the dirt, a straight line that possibly goes through the origin, might not. There might be a bit of systematic error, so I'm not going to worry about that. But line of best fit that fits all your data. And if you find that gradient, then that gradient will give you force over extension, F over X. If we go back to the other side, well, F over X is actually in the data, yeah? So that will give you a value for that bit. If you multiply it by L, if you divide it by A, then you will end up with the Young's modulus. Okay, so F over X is your gradient. So, have a play around with that. Send me questions if you're not sure, but you should be getting a value for copper that's fairly large. It will be gigapascals. So if you've got that, you know you've done it right. If you're a million out, then there's an issue and you need to come back to me and ask me why. Show me what you've done and ask me why. So write that up. It's going to be really important. It's about the only way we do the physical properties of materials. What is it that makes them behave to forces in the way that they do?